Hello, in this video I will introduce VL Interpret, which is an interactive visualization tool we developed at Intel Labs for interpreting vision language transformers. This work will be demoed at CVPR 2022. When training a transformer-based model for vision or vision language tasks, we often don't know what exactly the transformer is learning. For example, how does attention work within each of the vision and language modality or across the modalities? Why does the model succeed on some training examples or tasks, but not others? And more importantly, what aspects can we improve our model to make it better? To answer these questions, we need to probe the inner mechanisms of a transformer. Although such tools have become available for transformer-based NLP models, vision and vision language transformers remain as largely opaque models. Here, we developed VL Interpret to provide a single interactive system to interpret vision language transformers, which I will show you now. Here's a diagram for the workflow of our tool. As the encoded image and text tokens go through a transformer, we're interested in probing the attention heads, especially attention weights and hidden representations. For the hidden representations of tokens, we visualize the high-dimensional tokens as a 2D t-SNE plot for each layer. This plot shows interesting patterns in the distance and clustering among tokens. Next, as the transformer processes both vision and language modalities, there are four components of attention, namely vision to vision, vision to language, language to language, and language to vision attention. Our tool provides a novel interactive way to visualize these four components. For attention from vision, a heat map is drawn over the entire image to show the attention to a selected image token or a selected text token. Similarly, for attention from language to a selected token, we show a heat map over the text tokens. Now I will show the actual tool and a few interesting examples. First, here we could go to different examples to see how a model processes them. This chart on the top left shows the summary stats for attention heads in all 12 layers, and we can select which type of stats to show in this chart. A user could also show their own custom metrics here in this chart. For example, here we added a metric to show the correlation between attention from image to person tokens and the mask of those people. For now, we will look at the mean of cross-modal attention. As you can see, some attention heads have a higher level of mean cross-modal attention than others. Let's take a look at one of those attention heads. The graphs below will show the contents of this example, including both image and text. Now we can select an image patch, for example a part of the plants here, to show the attention to it. This image patch is heavily attended by both the text token plant and also the other plants in the same image. Similarly, we can select a text token, for example plants here. Again, a large part of the plant in the image and the text plant itself is attending to it. This shows that this attention head is pretty good at understanding the alignment between the same kind of object, both in the text and in the image. Here is another example. The text mentions heads and coats. Similarly, we see the image of coats and heads attending to this text. And here we can look at the average attention to heads in each layer by selecting in the mean column. We can see that in the early layers, the attention is more diffused. But in the later layers, the attention becomes more focused on the head area as it learns. This shows that the sense of objectness seems to be developed gradually in the model. We also see similar behavior in this model for some verbs. Here, for tokens like person 1, the attention from image is focused on this guy's face, but for verbs like staring and looking, the attention is clearly more focused on this guy's eyes. We made an animation button here to automatically scroll through the text and the attention to them. Here we can see that the attention from image is focusing on whatever the text token is referring to. For example, staring and looking get attention from the person's eyes. He and person 1 get attention from the person's entire face. Envelope and what get attention from the envelope. Besides attention, we can also see interesting things in this t-SNE plot of hidden representations. Here the red dots are text tokens, and the blue dots are image tokens. We can see that in the last layer, the text token of person 1 is close to the image tokens of person 1. And the other image tokens of the background are far away from it. In a different layer, for another example, we can see that the text token of people and the person token are relatively close to the images of people and far away from other images of known people. Going back to our hat example, when I click on hats, this token is shown with a yellow star on the t-SNE plot, and it also shows the closest image token from another example as a green star. We can see that this other image token is also a hat, indicating that similar concepts might be grouped together. So this t-SNE plot is another way of looking at how the transformer represents different tokens in each layer. It's important to note that all of the examples I have shown so far are examples where our model made correct predictions. And when a prediction is incorrect, we don't see this phenomena as often. Therefore, we have just used this tool to identify some of the model behaviors that are correlated with better performance. And it is possible that encouraging the model to perform more like this will eventually boost its accuracy. In summary, our tool provides a novel interactive way to look for behavior patterns of both attention and hidden representations in multimodal transformers. It can be adapted for any vision language transformer, regardless of model architecture or tasks. Therefore, we hope it will be useful for all of the researchers in this field to enhance transformer interpretability as well as performance. Thank you for watching.